Hi, today I'm going to go over the Raylib RPG example in this video. First, let's start off with the goals for this example. The main goal was to show common 2D game development techniques, such as tile maps, how to move things around those maps, and basic sound effects. These are like the core components of most common 2D games. The next thing that it needs to show off is how to manage game states. This includes things like menus, how to pause a game, how to resume a game, and how to run the actual game using states. Next, I wanted it to have a relatively simple project layout, not be very complex, not have a lot of classes or object-oriented code, just the minimum needed for the design I wanted. And I wanted the code to be relatively easy to follow. So it may not be the most efficient way to do things, but it should be a relatively easy way to see how to do something. Next, I want to cover the basics on how to build the game. Like all of my projects, this uses Premake. So you'd need to download Premake from the URL shown here. You'll need Premake version 5. You get the Premake for the platform you're on, either the Windows, Mac, or Linux version. You'll put Premake in the root folder of the game. You'll also need to get Raylib. The GitHub project for the example is set up with Raylib as a submodule, so you'll just need to update that. Or if you don't want to use GitHub, you'll need to put a copy of Raylib in the root folder in the Raylib folder. After that, you simply run Premake with either the VS 2019 or GMake2 arguments to generate the required make files. Then you can build the game. The repository does include a set of Visual Studio projects already, as well as a set of make files for Windows. If you are on Linux, you'll want to rerun Premake to get a new set of make files. Now we can go over the overall structure of the project. Everything starts with a main, as with most games. This main initializes 4 major systems. The first one is a loader. This is what handles loading of all textures and sounds. This happens at the very start of the game. It will show a loading screen to the user while we load all the textures and sounds. The next 3 things all work together to actually run the game. The big thing that we have here is the screen systems. This is what handles all the menus and HUD while you're in the game. So anything that's an overlay that the user can interact with that isn't the actual game will be handled by a screen. Then we have a game. The game actually runs the game logic while the game is running, and the game logic then updates a map. And a map is a collection of items, which is mainly a tile map, which is a grid of pictures that make up the actual game level. A list of sprites, which are all the things on the game level that can move, such as the players and monsters, and a series of effects, which are short-term animated effects, such as when a monster gets damaged or when you attack with a weapon. Okay, so now we can take a look at the actual code. Here we have the main CPP file, which is where everything starts. So just like any regular Raylib program, we set some config flags, we initialize our window, we call a function that sets up the window, that sets up the window icon and some other items, and target FPS, builds up the window icon, unloads the image for the icon, just gets us a nice window setup. We initialize our audio system, which simply sets up the audio, loads some background music, and sets a master volume. Init resources is where we set up our loading system. So as you can see, that's in the loading file. This is where we define what files we need to load. So we're going to load our tile map and an icon that we use for a logo. Then we're going to go and load a series of sounds. These are all put into a list of things to load. So we have a list of textures to load and a list of sounds to load. This does not actually load these items yet. We're going to do that as the game runs, so that the game doesn't sit there and do nothing while we load things. So because we're going to do this loading stage, we're going to use what we call a game state, or part of what's called a state machine. So we have a global here for an application state. If we go to it, we see that it is this enumeration. And this enumeration lists all the possible states that the game can be in. So we're going to start up. We start in our startup. Then we're going to immediately go to our loading stage. Now we do our game loop, which is going to run until the user closes the window or our state says we want to quit. We will set this state from things like menus in the game when the user clicks a quit menu. So we're not reliant just on the escape key or the close button on the window. So for every frame, we're going to go through and check and see what state we're in. When we start, we're in the loading state, so we're going to do an update of our load. So we're going to go to that function where we're going to go through and check. First thing we're going to check and say, hey, have we finished loading everything? If so, we're done. Finalize everything and return. If not, which is what will be when we first start up, we want to go through and load some things. This only loads a few things per frame. In this case, we're only going to load one. So we start by trying to load any textures. If we're done with textures, we start loading sounds. So this will go through and load all of our textures. Here we call our load texture, and then we're going to just store it in a list of loaded textures. And we're going to remove the pending load from the list. When we get to sounds, we're going to ask our sound system to load our sound file, which is going to load sound and put it in a list of sounds. So by the time we're done here, every texture and every sound will have an ID because it's stored in a list. So we have one set of lists for textures and one set of lists for sounds. This means whenever we need a texture or a sound, we can simply get it. So here's what we do for textures. We just say, when I need a texture, give me a texture, and we return a reference to the texture. That way we don't have textures spread all over the code. They're all in one place. Different pieces of code just ask for the textures when they need them. So as we can see, we do this same thing for each of the different states we're in. When we're in the main menu, we update the main menu. When we're running the game, we update the game. When we're paused, we update the pause screen. So every frame, we're going to update something. We have different functions here so that we can keep our code separate. We don't need one big update function that can do everything. We can keep everything nice and modular. After we do an update, we need to draw something to the screen every frame. So normally we go draw the map. The map is maintained independent of the game state, so when we're loading, we don't have a map, so map doesn't do anything. When we're on the menu screens, we'll have loaded a default map to just show in the background, and draw map will keep that. When we're playing the game will have loaded specific maps, and we'll show those. In this case, a map is more than just a tile map. It's also any sprites for monsters and players, and any effects that happen, like casting a spell or attacking someone. On top of the map, we then draw the screen, which will be any menu overlays, so all menus and the game HUD are handled as a screen. We go through and look for the current screen, which is just a pointer to a screen object, and we tell it to draw. This is one of the few cases where object-oriented programming was used because it made sense. There is a screen is a pointer to a screen. A screen is a base class that has a draw function and a few utilities for things like to find out if a button is hovered, to draw some centered text, to draw a button, and to dim the screen. This common code was needed by multiple different menus, so it made sense to put it all into a base class and call that. Lastly, we update our audio and end drawing as normal. Then when we're all done, we clean up. The main things that most people will be wanting to know about is update game. If we go to update game, which is saved in our game.cpp file, it is a simple function that goes through and figures out what the game needs to do on any specific frame. The first thing we want to do is check and see if the escape key is pressed. If the escape key is pressed, we want to do one of two things. If we had our inventory screen open, we want to close it. Otherwise, we want to pause the game. When we pause the game, we go back to our main and we change our state to the fact that the game is paused. So this will no longer call our game update, but instead call our pause update. This is how we're able to keep our game state paused and nothing changed. It hasn't been destroyed, it's just not being updated. Along that line, we keep something called a game clock, which is like the regular Raylib clock, but it only gets updated when the game is running. So when we're paused, we won't come in to update game, and we won't update game clock. This means we can track the last time things are done, such as the last time someone attacked or the last time someone moved, and that can remain consistent even when the game is paused in between. So now that we have our clock, we go and do just the various actions that the game needs to do. First thing, we see if the player had any input. This checks for various clicks on the screen, checks to see if the point that was clicked is on the map, if it was clicked on a treasure chest or a monster, and sets the appropriate flags to do the appropriate action later in the game. So when we're done with this function, we know either where we want to move or what we want to attack. Then we're going to apply any motion. So if the player wanted to move somewhere, we figure out where they want to move, find out if that point is actually in the map, and then move them to that point. During the movement, we check and see if they're on an exit. If so, if they're at the end of the game, we end the game and tell them that they've won. If they go to an exit that goes to a different map, we read that data from the map file, and we then switch to that map file. Then we apply any player actions. This is where we would resolve attacks. So if you've clicked on someone, we'll check and see if we hit them, how much damage we did. We'll play effects and sounds to show that they've been hit. We'll check to see if the player clicked on a chest, and if so, we'll open the chest and tell the chest to drop any loot that was in it. Then lastly, we'll go and see if we actually ran over any loot items to pick up, and if so, we'll pick them up and remove them from the map. Next, we'll go and update any monsters. They always go after the player. So the first thing we do is check to see if any monsters are dead. So we go through our list of monsters, looking for monsters who have a health of 0 or less. If so, they're dead. We tell the monster to drop its loot. We remove the sprite from the map and add an effect of the monster dying, which is just a little thing where the monster spins and fades away. And then we erase the monster from our monster list so we won't process it again. Once we've got rid of everyone who's dead, we go through and see if any monsters want to move. So we check and see if they've been triggered. If they haven't, we check to see if someone's close enough for them to be triggered. If they are triggered, they just try to go attack the player. So this goes through, checks to see if they're close enough to the player. If not, moves toward them. If they are, it will try to attack them, and this generates all the attack effects. Then we check to see if the player died, because this is after the monsters have attacked. So if the monster attacked them and killed them, the game ends, you've lost, and we tell the score. Then we go through all of the monsters and players and update the map. So the game keeps a list of monsters and a data for the player that is independent of the map. This is all game state data. It's stored with the game. Not necessarily with the map. So this means that the game can run without any graphics. This is usually a good idea so that your game state can be maintained regardless of what is drawn. Often you'll have things that need to be updated that might be off the screen. So like you might have a monster that's very far away that needs to be updated to go chase the monster. You don't want to update that when you draw because he may not be visible. So you still need to update him, but you don't need to draw him. So the main thing we have in our game header that's shared with different components is our player data. This contains all of our position data, what sprite the player is using, where the player clicked, what sprite we're going to use for the click, how fast the player can move, how much health the player has, how much gold they've collected, when the last time they attacked was, do they have any buffs from items, what equipment do they have. And then a few callbacks, which we'll get into later, that come from the user interface for when the user clicks on the inventory. So once we've figured out where everything is in the game, we know where all the monsters are for this frame, and we know where the player is for this frame, we need to tell the map where everything is. So we've maintained a sprite in the map, which we'll get to in a bit, for the player and each monster. So we go through and update the position of that sprite to where the player is now. We check and see if the player has changed any armor. If so, we pick the right player sprite. And then if the player has clicked on something to move to, we put a sprite where that player goes. The last thing we do is we just go through the monsters, find their sprite in the map, and update them to the current position. So on to the map. Our map is a collection of things. It is a tile map that is used to draw the actual game world. It is a list of sprites and a list of effects. So we have our map.h file here that includes the interface that the game can call with the map. So we can tell the map to load a specific tile map. We can get rid of the tile map, and we can tell it to draw the map. The map maintains a camera for where it is on screen. We can get that camera because we might need to know that data for when we click on things. We have a function here to set a visible point. This is what's used to keep the player within a certain rectangle on the screen, even if the map is bigger than the world. These functions here return lists of objects from the map data. The map contains things like walls, monster spawns, player spawns. These functions are used to read the data from the tiled map, bring that out so that the game can know, here's where I need to spawn monsters. Here's where all the exits are. Here's where all the treasures are. This means we don't have to hard code these pieces of data into the game. We can simply read it from the map file. We have some functions to help tell us collisions in the map. Is a point in the map in a wall or not? And do we have a ray that's going to hit the map? This is used for doing attacks, ranged weapon shots, and motion. We also maintain a list of sprites. So for each sprite that is on the map, it has a sprite instance. So it has an ID, it has whether it's active, it knows what frame in the sprite tile map to use. It knows the position it's in, what color it is. We have a little thing here called bobble, which tells the map to jiggle the sprite up and down to animate it a little bit, and whether or not we want this sprite to have a shadow. So we have functions to add sprites, updates the sprites, remove the sprites, and clear the sprites. This is how the game logic adds things to the visual map to show to the player. Then we have effects. They're like sprites, but they're temporary, and they're always animated. So we have effects that will just fade something out over time. We have something that will fade it out and make it rise above the position we specify. We have something that'll rotate and fade out. This is used for death. Rise is used for damage. Scale fade is used for attacking. That will scale the item and then fade it out. And to target will take a sprite and drive it from a point to a target. This is used for ranged attacks. So our map loading is done in multiple stages. First, we read the tile map. This is done using a XML tile reader. So we read the XML of the map from tiled. We parse the XML and we fill out a structure. The end result is what we call the current map. It is a tile map object, and it contains all the map layers and all the map objects. I'm not going to go into too much detail to this, but the code is all here for how to read a tiled map. It's relatively simple, and there's code here to read it and draw it. This sets up the map camera, figures out how big all the layers are, and centers the map on the screen when we start. We check the map to see if it wants to play any background music. If it does, we play it with a property. Drawing the map is a similar affair. This is where we begin our drawing mode with our camera. We draw the tile map, which goes through all the tiles that are visible, pulls them from the tile map, and draws them on screen. The tile map is pretty basic. It is a list of tiles in a sprite sheet, each separated by a gap of 4 pixels. So the tiled map references these indexes 0, 1, 2, 3, 4, and builds up the level using this. When we imported this texture, we said it was a tile map, and we told it how many sprites were in it. So we said it's 14 wide by, I think, 12 high. The code does the math to figure out how big each sprite was, because we told it how much distance is between each sprite, and it computed a series of source rectangles for each different sprite in this list. That's all handled in the sprites file. This is where we loaded sprite frames. We can also do things like set sprite origins, because not all sprites use the same origin. The tile maps sprites all use the center origin, but the players want to use, the tile maps all use the upper left origin, and then all the players and monsters and items want to use the center origin. So we have a function to go through and set the origin for all the different sprites that we need. We store this sprite info structure for each sprite. This includes what texture, what ID it is, what texture ID it is, so that we can go get the texture when it's time to draw it. It includes the source rect and the origin, and in a few cases we use the npatch sprite system to draw the user interface, so we need the set of borders. Most of the time this is not used. So back to our drawing. After we've drawn our tile map, we go through all of our sprite instances and draw them. If they want the bobble, we apply the bobble using the sign function and a global time. Note this does not use the game time, but it uses global time. This allows the animation of the bobble to proceed even while we're paused. If we want to draw a shadow, we first draw the sprite offset from its position, and we color it black, so it looks like a shadow with a little bit of alpha texture. Then we draw our sprite. Lastly, we go through the list of effects, figure out what each effect is, and we draw them. So they're drawn with sprites with some parameters. So we just have a little switch statement that determines what the alpha will be, what rotation, what scale it will be, and we use the lifetime. So we know the maximum lifetime for the effect and the current lifetime. This increases as we go. So we use that parameter to figure out how far along the effect is. So the last thing we have for drawing is screens. These are drawn on top of the world. Here's an example of the game HUD screen. We simply draw the user interface that is shown. So we draw a health bar. We draw the current weapon they have. We draw the any activatable items they have, and a button to click the backpack to open it. This is all just drawn here. You can go through this code and see it's still drawn using regular sprites and text and regular Raylib calls. We're drawing rectangles, we're drawing text. So that's a pretty much an overview of how the basic game works. My recommendation is if you have a debugger, put a breakpoint in the section of code you're interested in, run the game, and watch what the code does when it gets there. You can follow through the code pretty straightforward by going through all the functions. You can start at the main and get into either the game or the drawing, whatever you need. There are logical functions for every action. We have move player. We have pick up item. We have remove item from inventory. We have drop loot. You should be able to find a function that's named what each thing does, and you can follow through it. This video is getting pretty long, so my recommendation is just go through the code, and if you have any questions, please ask in Discord. Good luck and have fun.